Welcome to this presentation on the analysis of 2D elements, in particular applying it to a heat transfer problem. We look at the stiffness and load matrices, the development of those, and an example using ANSYS Mechanical to do a thermal analysis. All right, so to set up, you can go to lecture materials. Again, the link for that is in the notes below. Grab the notes for ANSYS of 2D heat transfer problems. And you can also get this SolidWorks file, chimney and heat sink parts. There's two parts in there that we're actually going to use, the chimney, the concrete part, and the brick part. There's another one in there that may or may not be used in a future example, but you'll get that. That's all in a zip file, so just unzip that and you'll be ready to go. All right, so where are we going today in this lecture? We're going to look at the 2D governing equation for a heat transfer problem, strictly conduction in this case. The formulation of this problem, how we would solve it using rectangular elements, and how we would do that with triangular elements. And then we'll do an ANSYS example to finish out. All right, so the modes of heat transfer, we have conduction, convection, and radiation. But when we're in a part, when we're in a fluid, there's always some form of conduction that's moving things about. And so that's what we're really going to focus in on this problem. Convection and radiation will come in with boundary conditions. So we're going to focus in on the conduction here. So from Fourier's law, the heat transfer rate is defined by Q, or the heat transfer rate, is equal to the conduction coefficient times the area times the temperature gradient along some direction. So in this case, the x direction. And we also have it in the y direction, because at least for a 2D case, we're going to have both of these showing up. So the conduction heat transfer rate in the x and y directions are represented by the lowercase q's. Thermal conductivity of the medium is K, and cross-section area of the medium is A, and the temperature gradient, the del T del X and del T del Y, which I forgot to include here. All right. So the actual governing equation then for 2D steady-state conduction is this. So we have the conduction coefficient out front in the x direction times the second derivative of the temperature with respect to x, plus the conduction coefficient in the y direction times the second derivative of the temperature with respect to y, plus this new term that actually wasn't in the Fourier's law of conduction. That's the heat generation per unit volume. So if a volume that energy is flowing in and out of is actually generating heat, then we would include that term. That's actually something we won't be looking at here, but would show up in the general equation. All right, the area disappears because we divide through by the area and goes to 0. So that's our steady state conduction equation. So looking at some various boundary conditions we could have with this equation, we could have constant surface temperature. So usually this is due to a fluid phase change, such as condensation or evaporation. And so there we have the temperature at some location, in this case x equals 0, will be equal to some constant value. We could have heat loss or gain at the surface be neglected, so some type of insulation. So the temperature gradient at that location, in this case x equals 0, that gradient would be equal to 0. So that would represent no loss or gain from that location. A constant heat flux on a surface. So if we have looking at the conduction at that surface on one side, will be equal to a constant rate of heat flux. And a good example of this would be a burner on a stove is set to a constant heat flux. Heat loss or gain at a surface by convection. So the conduction into or out of the surface is going to be equal to the convection to or from that surface. So it's the temperature at that surface at x equals 0 minus the temperature of the fluid. Give us that the overall heat transfer loss. Heat loss or gain at the surface by radiation could be another case. And both conditions 4 and 5, I've got the numbers, but this would be 4 for the convection and 5 being the radiation. All right, so we could have any of those cases, but what we'll focus on here is convection as we go through. So linear rectangular elements, again, if you want a more kind of initial run through of this, this is in the previous presentation, which I'll leave a link for below in the notes. But we're going to look at this linear rectangular element, nodes I, J, M, and N in the X and Y direction locally. And you can see what the overall temperature profile might look like on a given element. All right, so the equation for nodal temperatures within a linear element is represented by the shape functions at each of those nodes times the temperature at each of those nodes. That will give us the overall temperature within the element. And those are the shape functions. Again, we developed this in the last lecture. Shape function node I, J, M, and N. And this is on a global coordinate basis. So the Galerkin approach says the idea here is we want to reduce the residual error, or the residual to 0, force it to be 0. The Galerkin uses an average with a weighting function the same form as the solution equation. So our weighting functions are the shape functions. The shape functions are from our solution equation. So we'll have 4 of those, 4 residual equations. So we have the residual equation for node I using the shape function node I, and there's the governing equation. All right, we differentiate or integrate that over the area, and that all needs to be equal to 0. So we'll do that for node J, M, and N as well. All right, so we're trying to apply our linear solution here to our governing equation. All right, so in matrix form, what we come up with is the transpose of the shape functions. If the shape functions is a row matrix, so it would be the transpose of that, times the governing equation, all that integrated over the area. All right, so we can separate this into 3 integrals, one for the conduction in the x direction, conduction in the y direction, and then the heat generation term. And we could generalize this and set C1 is equal to our Kx, C2 is equal to Ky, and C3 is equal to Q dot. And our phi, or psi here, is equal to the temperature. All right, so we get our overall general equation now. So we got the transpose of the shape functions times our first term, second term, and then this was our generation term, some constant value there. So now I can apply to other problems, not just temperature, that have similar governing equations. And since we're integrating over an area up here, right, so dA, integrating over that area here, we need to perform a very complicated double integral, because we actually want to integrate in respect to in the y direction and the x direction. All right, so a little bit more is involved here in integrating over the area as opposed to just a length in the previous case with 1D elements. All right, so the resulting stiffness matrix that we come up with as a result of in doing the Galerkin approach there is this. So the overall stiffness matrix for conduction is that C1 value that we had times the width over 6L, and then you can see what the values there in the matrix. Then C2 times L over 6W with all those values there. So we got the length and the width of our rectangular element on its sides. So then we substitute back in for C1 and C2, and as we do, we get the conduction in the x direction times the width divided by 6 times the length, and we get the conduction in the y direction times the length divided by 6 times width, and the overall indices inside these two matrices. So for any element that we have that has conduction through it, we'll use this equation to look at how the heat transfers through that element due to conduction. All right, so let's apply some boundary conditions. What do those look like? All right, so any convective boundary condition along different edges will contribute to the conductance matrix. So we added in to the matrix we just came up with the 2 terms for x, conduction in the x direction, and conduction in the y direction. It would add into those matrices, that contribution there. All right, so if we had convection here along the length where we have nodes I and J, we would include this information because this is functionally, we have I, J, M, and N. And then if we went to the other possibility, we could have convection along the side or the edge where J and M exist. So remember the unit looks like this. We have I, J, M, and N here. So it would be along this side here. It would be this case. So we'd include these terms here. So we have I, J, M, and N. So we're just including those terms in the middle there. All right, if we have M and M, so now we're up here on this edge here. So we're just going to include these values down here in the corner. And if we're at N and I on this edge over here, then we have just the ones in the corners of our matrix there. All right, so those are the contribution. If we have convection on that edge, we'd include one of these 4 stiffness matrix into the conductance one. All right, for loading, the load matrices along the edges due to convection. So we have to include some load aspect because that's going to include the fluid temperature is going to show up. So again, if it happens on edge IJ, we'd include this one. For edge JM, we'd include this one. For edge MN, we'd include this one. And for edge L or NI, we'd include this one. All right, so you include those in the analysis to solve for temperatures. If we had heat generation, so any heat generation within an element will contribute to the thermal load matrix for the element with this. So we have the overall, here's the Q dot for that particular element times the area divided by 4, and then we have a straight one column matrix here to include a contribution of the heat generation to every node within that element. All right, and then we can put those together and just solve it out. So that's how we can solve for when you use the rectangular elements. So that's rectangular. So let's go look at linear triangular elements. The formulation we have here. So again, the overall setup here using global coordinates. We have I, J, and K. And then you can see kind of a representative temperature profile we can have on that. All right, so again, the equation for the nodal temperatures within a linear 2D rectangular element is the shape functions times the temperatures at each node, and we have the shape functions at node I, J, and K. Now the difficulty here is we have these extra alpha and beta terms, so we have to include all those. It gets a little bit more hairy, but I'm trying to simplify things as we clump things together. Again, using the Galerkin approach, so we can take the transpose of the row matrix of the shape functions and multiply that times our governing equation, integrating that over the area, in this case the triangular area. So the stiffness matrix for conduction comes out to be this. So we have the overall conductance matrix because of the conduction in the x direction and because of the conductance in the y direction. And where area A is the face area of the element, the overall area of our triangular element. If we have convective boundary conditions along the different edges, so if we have for edge IJ, so we got a little triangle here. It's a little bit more straightforward here with the triangle versus the rectangle, but I'll draw it up here anyway. All right, so for along this edge right here, this is what we'd apply, right? Because again here, if we go, we'd have I, J, and K. Oops, I, J, and K. So we'd include these two, or these four here for I, J, for I and J. If we're on the JK edge, so we're on this edge, we're going to include just the ones down in this corner. And if we're at the KI edge, right here, we're going to include the ones up in the corners, 2, 3, and 4. All right, so those will be added in to the conductive matrix, as we did with the rectangular element. For the load matrices, all right, so we got to include that. We have the thermal loading here. So for, again, on edge IJ, if we have convection along that edge, all right, we'd add in this forcing function. If we're on edge JK, we do this forcing function. Again, so if we can look here on the side here, we got this I, J, K effectively. And so just I and J are included there. Here just J and K, and then K and I here for the last one. All right, so depending on if convection's on that edge, we would include these terms. Now again, heat generation, you can imagine from what we had from the rectangular case, so we got our Q dot times the area divided by 3, and we got it included at each node. All right, hopefully pretty straightforward. We're going to solve it the same way we did the rectangular element and finish that out. All right, so now let's look at the ANSYS example. So we'll kind of see how this all works together, applying the boundary conditions. ANSYS, we don't have to really do the matrix math, so that's kind of nice. But we can do this work a little bit quicker and let the computer help us out here. So we're going to look at a couple different things here. If you want to skip to those things, the notes, feel free to look at that. But I'm going to take it step by step and hopefully get some extra tips here on how to use ANSYS and analyze different things there as well. So overall here we have some concrete interiors. So this is a cross section of our chimney. So we're looking essentially down the chimney in this case, or up the chimney. So we have concrete here, the initial 1 inch. And then we have our outer brick that goes 26 by 26 inches. And I've drawn these pieces again. They're in that zip file if you can get it from the lecture materials. See the link below. and you can grab that and do this along with us. All right, so I'm going to go right over to SolidWorks that I already have open. And I'm going to create a new, this is a little bit different here because I already have the parts, but I'm going to create a new assembly, not a new part. So click on assembly here and OK. All right, so it asked which documents you want open, so I'm going to browse. And let's start with the concrete first. So I'll click on the concrete part and open. And if you bring it in here, you can see that you're there in the middle, right? It's swinging around. I don't want to just click anywhere, so I want to get it in the same spot because I want to line them up just right. And this is something I've done ahead of time, and we'll talk again more about later how to do this. But I'm just come up here and click on the green check mark because that's going to put it right at the origin. All right, so right at that spot there. All right, I want to add the brick now. So that's the concrete I want to add in the brick. So I'm going to come here to insert components and browse again and come back here and get the brick. So click and open and see there's the brick. So I would just put in here and I have to mate it and get it all in the right spot. I just want to get it. I'm not worried about that today. We'll talk about that later. So just come in here and again green check mark. I'll put it right at the origin and it puts it in the exact spot I want it to be at on there. All right, so now we're ready to analyze this. That's all we really needed to do. So we could just take this right over to ANSYS, and we'll go ahead and do that. So use my ANSYS integration here. And actually, I just realized I didn't save the part, so this is probably going to fail. So we'll just see what that failure looks like, and go back and fix it here then. So yeah, so it says right here, I don't know what geometry you're talking about. All right, so let's go back and do the SolidWorks here, and we're just going to go ahead and save this. And yep, save all. So it asked me what's my assembly name, and I'll just call it the chimney. And save. And now go back to ANSYS. I'm going to right click on geometry here. I need to left click there. Try right clicking again. Nope, that blew it up. All right, so it doesn't like that. Let's try it again from scratch here. Now that we've saved it. There we go. Selected that time. All right, so we want to do our analysis now, drag our analysis in. So we're going to do a steady state thermal analysis. We're looking at steady state here, so it's going to click and drag it in. Drop it right in there. All right, so we have the geometry here. So we're going to drag it over and link those two. That looks good. Come back up here to engineering data. So double click on that. And obviously structural steel is not what we want. So we're going to need to come in here and go to the engineering data sources and find some stuff that's going to work for us here. So let's look at general materials first, so you see what we come up with. And let's see, I think they have concrete here. Yep, there's concrete, so we'll add that. And let's see about brick. Do they have brick in here? Let's see it there. It's not linear. We don't want to worry about that right now. Thermal materials. So they don't have brick, looks like. So what we're going to do is we're going to have to create a new one. All right, so let's go get back to our materials here. So we're going to click right here. We're going to add a new material. We're going to add brick. So just type it in there and hit enter. And it comes down here, and here are the properties for brick. All right, there aren't any because it hasn't been defined yet. So if I come over here to the left-hand side and expand thermal, I want to put in the isotropic thermal conductivity. All right, so I can add that in here, drag it down, drop it there. And so I can put in the value here. So from our sheet, though, we are in BTUs per hour, inch squared degree Fahrenheit. So BTUs per hour, we don't have inches, so we have feet squared per hour. So we want to do the second one here. All right. So we want to make sure we put in according to the units. So we got to go from, bring up the calculator here. So we have K for our brick is 0.04, and so that's per hour. And so we want to divide by, oh, I'm sorry, it was in feet. It was feet issue, not inches. So we got to go from inches to feet. So we got 12 inches. So we want to multiply by 12 to get over to feet. So we got 0.48. So we'll go 0.48. All right. Should be good there. All right, let's check out what concrete is. So concrete's 0.72. That's in, whoops, that's in watts. We don't want that. So we'll come down here and look at, we have there. And to confirm, let's kind of back calc this one. We're going to go the other direction. So we'll do calculator here, and we got 0.41601. And that one's in feet, and we want to take it to inches. So we're going to divide by 12. And we get 0.03, which is not super close to the concrete. So maybe you want to update this one. We want this to be 0.07. All right, so let's fix that. So 0.07, that's in per inch. So again, multiply by 12. So that's 84. Okay, so let's update this to 84. Oops, 0.84. All right, so that looks like we should be good there. All right, so check our brick, 0.48. That's good, and then our concrete is 0.84. All right, so we got those. Let's go back now, so we can just go ahead and close that and go into our model. Double click there. All right, that looks good. So let's apply materials. Here we're going to just work our way down the left-hand side here. So geometry. We got the concrete. So concrete comes down here with the material assignment. Make sure we're on concrete. There we are. So that looks good. Go to chimney, brick. Change the assignment over to brick. That looks good. And you can check to see it's still concrete, still brick. All right, so we're not worried about meshing quite yet. Let's get the boundary conditions applied. So we just have convection on the outside, and we have convection on the inside. And this just is insulated here. This is basically just a cross-section slice, so we'll just keep this as insulated. And so it's just convection on the inside and the outside. And so let's go into thermal, so we can get convection. Up here is our boundary conditions, so thermal boundary conditions here. And so we're going to play it on the outside first, so we get click surface. And you see how we can't click more than one surface by just clicking. So I'm going to hold down Control, and so I can click more than one surface, and I'll just rotate it around, click these other two. And then I'm going to hit Apply. All right. And we got the film coefficient. So this is nice because, look, it's in BTUs per second inches squared Fahrenheit, which is what we have from our, at least on our handout, on the outside. So outside surface is 0.12 BTUs per hour. Oh, now it's in seconds. Of course, everything keeps switching on us. I thought it was quite. All right, so it wasn't an hour, this is in seconds. So let's just see if we can kind of help ourselves out with units. It's going to take it over to feet. Let's just see here. So we're feet squared versus seconds. Yeah. So it really doesn't help us by changing units there. All right, so we got to update this one as well. So we got from seconds, we got to go to hours. So let's see here. So we have it in hours. So 0.012 is in hours. So we'll multiply by 3600 to get over to seconds. Oh, to get there. 0.012. It's in per hour, so we need to divide by 3600. Yep. All right, so we got, so 3.33 10 to the minus 6. All right, so let's see, we're going to go 3.333 e to the minus 6. Looks good, so I can take the e value there. Ambient temperature is 10 degrees Fahrenheit. So I'll type that in there. All right, so I think we're all good with that one. All right, so let's go to convection again. And now it's interior surfaces. So hold down Control, click all those surfaces, and we'll click Apply. Come down here. Oh, I gotta fix that one. So the interior H is 0.037. That's per hour. So we're gonna go to seconds. So divide by 3600. So 1.02. Now let's just copy this guy. So come down here and paste. And get rid of some of those sevens. All right, and then ambient temperature is 140 degrees Fahrenheit. And that looks good. All right, so let's come back up here to mesh. And let's see what we get. So we'll just run first mesh, see what it looks like coarse-wise. Yeah, so that's pretty coarse there. Let's see what the statistics show us here. Can't go over, oops. Can't go over 256K nodes, so we're okay there. So let's relevant center, let's go to Find here and update. See what we get here on the mesh. All right, so that's better, 190. So we're not over. Still not great. I mean, probably good overall for in the center, but if we have some strong gradients, we're going to want to refine that a little bit more. Let's run this for what we have right now. So we'll go ahead and go to Solution, and we'll want the thermal plot, so we might as well just get that now. So I'll come in here and get the temperature plot, and let's go ahead and solve it. So what I did right there is I just right-clicked on temperature and clicked on Solve. All right, so you can see what it looks like there. It's right on the XY surface. So working outward there from a min near 20 to a max near 124. So again, we have convection. So the air temperature out here is 10 degrees Fahrenheit. And in here, it's 140 degrees Fahrenheit, but not actually at the surface. So it makes sense that the max and the min are a little bit higher, or lower and higher respectively from the other ones. All right, so that would be one way we could do it and get to that point. Now, the thing you can see here is, notice how round it is, right? There's a lot of symmetry we can exploit here and not have to mesh that whole chimney and save us a lot of computational time, though this one doesn't take that long. But if we wanted to add more nodes, more elements, to refine out some thermal gradients, then this would take us a much longer time we wouldn't need to. So let's look at symmetry now and see if we can exploit that a little bit here. So going back to our SolidWorks model, actually go back to ANSYS real quick. We can obviously see we could cut the sucker in half, right? And we'd have some symmetry as both halves are the same. But if we didn't half, so we just have this, say that we just have the left-hand half. Well, let's do that real quick. So we're going to come back here to SolidWorks and we're going to cut this sucker in half. So we'll go to Sketch first and click on Sketch. And it says, which plane do I want to sketch on? Well, let's find a plane that's already in the middle. So let's do the right plane. So it's right there in the middle. So click on right plane. And we're going to look at it from this side. And we're just going to create a box that's going to be around the whole piece there. All right, or rectangle. And then we turn to the side here so you can see it cuts it, slices it right down the middle. But we want to get rid of this one side. So we can still stay in sketch, that's fine. Go over to assembly, assembly features and extrude cut. All right. We want to cut away this right hand side. We don't want it to go to the left. We want to cut away the right hand side. So we're going to flip our cut. So it's going the other way. And then we want to do through all so we get rid of everything there. And then we'll do the green check mark so we get rid of the one side. All right. So we just have the one half here. Now going back to the ANSYS model, we just have that one half. Wait, we could cut this again. We could cut it right here, and we'd have symmetry all up in this area, in this quarter. All right, so let's do that. Let's cut it again right along here. All right, so we've got to find a plane there. So we'll come back to our sketch, new sketch, and which one of these? Ooh, that one right there, top plane. So if we cut across that top plane, we'll get rid of that bottom half. So I clicked on the top plane. I'll do my rectangle. So let me reorientate this. So I'm looking right down the top. And we click here to make sure I click far beyond it. So I encompass the whole piece there. And I'll select OK. And then come back here and see, yep, it's going to slice right through it. So we'll go back to assembly, assembly features and extrude cut. And go in the right direction. I'll just say through all. To take that out, green check mark, gone. All right, now I've just got this last little quarter. I went from this whole thing to now I'm down to a little quarter. All right, but let me go back here. What if I cut it one more time? All right, I've got this little quarter right up in this corner. I could cut right here. I got symmetry across that corner there. Let's do that. So that's going to take a little bit more work here. What we don't have is we don't have a plane that we can draw a rectangle on that goes in this direction. We have to create a new sketch plane that would allow us to go this way. So the way we do that is we have to create an axis on which to rotate on. So I'll show you how to do that here. So we'll go back to sketch and we'll click on sketch. And what surface do we want to be on? Let's just be on this, this top plane here. And we're going to draw a center line on that. And the center line is going to be right here. And we'll start at the origin. And we'll come here and make sure we're at 90 degrees. So we want to make sure we're right on this angle here. And so right 90 degrees right there, okay? So we come along here. Doesn't matter really the length at all where we end up. It's just we're going to use it as a rotational piece. All right, so you can see where it's at. It's right below this top edge, and it's in line with the side here. So let's look at the front plane here. All right, see where it's located. All right, and so now we can create a new sketch plane. So let's do that. So we're going to exit sketch and go to a new sketch, and we're going to edit sketch. I'll click on this. We'll just do a new plane. So it says, what's the first reference point? Well, we're going to reference it off the top plane. And the second reference it's going to look for over here on the left. We're going to click on the axis. So we might have to zoom in here a little bit, make sure we're getting our axis center line here. All right. So now it's starting to draw the plane there, the yellow plane. And it says, oh, what angle do you want this at? Well, I want it at 45 degrees. All right. Oh, but I don't want it going that way. All right, I want it going this way. All right, so I just need a reverse direction right here. So I select that and then get it to go the other direction. All right, and then it looks good. Now in the corners here, you can see you can drag these out and make the sketch plane bigger and smaller. I really don't care. I just want to have the sketch plane go in the right direction. So I'll just leave it right there where it's at. All right, so once we have that plane drawn, we'll go ahead and exit. And instead we want to draw a new sketch on there. So let's come back in here and we'll draw a sketch on that new plane. So I select our plane there and drawing the box. Again, we'll orientate so we get it the spot where we want to get the cut to go through. All right, so make sure we get the entire part encompassed. Looks good. All right, so now we can go over to assembly and extrude cut. All right, and we want it to go through all and green check. All right, so now we're just down this little bitty eighth of our original piece now. Let's zoom in there. All right, so that's what we want to take into ANSYS. So we'll go ahead and save this. And we'll go over to ANSYS and we'll update our geometry. So right clicking here, we're going to update geometry from source. Click on that and let it do its work. All right, there's the piece. And looking over here on the left-hand side, let's check to make sure the convection boundary conditions are in the same spot. So we'll see convection here is the 10 degrees. That's on the outside. Oh, still got it selected, so that's good. How about convection on the inside? Still got that one selected. That looks good. All right, let's make sure the materials are still good. So the chimney, concrete is concrete. And the brick is still brick. Looks good. All right. So let's go to our mesh. Let's see what the mesh looks like if we update that. All right, see, obviously it's much denser now than what it was before. And so all those nodes we had in the whole body are now all in this one piece here. So you can get much more dense mesh and still get the same information about what's happening. So we'll go and come in here and we'll go ahead and solve for our temperature profile. And see what we get here as a result. All right, so there we go. So we got the kind of that roundedness that was happening, and so it rounds into this other symmetry half that would have been over here, as well as the symmetry half that was over here. And we're able to do it all, and you see the temperatures coming out very much the same as what we saw in doing the full model. All right, but much smaller, and we could probably use the same number of grids that were there originally on the original model. It would run much faster because there'd be less nodes overall because of the symmetry that we cut it down to. Right, but hopefully you get the sense of what that symmetry can provide us and how to get there, cutting things down in SolidWorks. Hope you enjoyed this presentation. Let me know in the comments if you have any questions, and I'll see you at the next time.